Okay, let's have a look real quick. We'll, like I said, we'll take a little time at the end, and maybe we'll look at some questions, etc., etc. But everybody, have a look up here for a second. I want to show you something here. We're going to remind you about something you've already talked about, dilations. So let's put dilations in the context of stuff. I'm talking now, please, so I'd like everybody else to stop. Thank you. Let's put this in the context of some other stuff that we've talked about, right? We spent last chapter talking about isometries, right? We looked at all the kinds of transformations that preserve all measurements, right? Reflections, translations, rotations. Okay, there's another kind of a transformation we're going to look at that does not preserve measurements. In fact, it's intended to change measurements. A dilation, right? A dilation is going to, what a dilation does, in a sense, it's like on a camera, it's like using a zoom lens, right? Things are going to get bigger or smaller depending on which way you twist the zoom lens on the camera. Okay, but everything stays the same shape. Only the size of the measurements are going to, of the sides of like polygons are going to change. Angles stay the same. Side lengths are going to change proportionally, right? So what's this look like then? So a dilation, there's a couple parts of a dilation we want to be aware of. One of them that we might anticipate is a scale factor. Right, we just spent a bunch of time studying similar triangles, right? And one of the things that you done a lot of work on is determining what the scale factor is that relates to similar triangles or similar quadrilaterals or whatever we happen to be talking about, right? So we need a scale factor. The other thing, though, is there needs to be a center to the dilation. And I think I have a really good way that I like to visualize this. I think you'll like. So if we're going to, you got to go for just a second. So if we're going to do something like, let's just say we're going to have a triangle. Here's going to be where we're going to point the center of the camera lens. Okay, we're going to call that C. So that's going to be what's going to be the center of the dilation. It's where we center our zoom lens. If this is our original triangle that we're going to zoom in on, what's going to happen to this? And just use your experience with video cameras or cameras to tell me what I should expect to see if I focus, put the center of the lens right there, and I, for example, zoom in. Raise your hands. There's two things that are going to happen. What's one of them? Okay, it's going to go out of my view. In which direction is it going to migrate? It's going to migrate away from the center, isn't it? Right. So it's going to move in that direction. That's true. What else is going to happen? What else is going to happen?
The triangle will expand.
It's going to get bigger. Yeah. So we're going to get something like it's going to do something like that, right? It's going to get bigger and move away, right? Everybody agree?
Yeah.
Okay. Do you think you could develop some relationships there? Let's label some points here too. Let's say, for example, let's say this is point X, Y, and Z. And so this would be what? X prime, Y prime, Z prime. Can you establish some relationships here? Perfect. Okay, so that's good. So what Daphne's saying is we know these are then similar triangles. And so all of the relationships we had before with similar triangles exist. Perfect. So we know, for example, that x, y over x prime, y prime equals x, z over x prime, z prime equals, what did I forget, yz over y prime, z prime. Very good. Anything else? Any other segments that maybe aren't drawn there? What do you think?
Distance of the triangles from C.
Okay. Okay, so what about something like this? What if we said something like CX, and if I had drawn this right, and I didn't, if I had drawn this right, I guess I probably need to make this one a little bit smaller. This isn't going to be exact, but if I continue this segment out, like so, let's see, this distance right here we'd call CX, right? What do you think the distance CX compared to CX prime is going to equal?
1 to 2.
It's going to be, okay, it's going to be the same as, it turns out it's going to be the same as any of those, right?
Same scale.
Same scale factor. And I could also compare it to something like CZ, and so here's where I got it, this is the wrong size. So, I don't know, about like that-ish, maybe,
Yeah.
see?
So that continues to be.
It's going to be close enough. Oh, how that happened. So then CZ over CZ prime would also fit that, wouldn't it? Okay. So that, honestly, that sums up a dilation right there. That's a dilation. So we would say that this is this scale factor going to be bigger than 1 or less than 1? How come? Because we went from small to big. Yeah, because it's an increase, right? Okay, now if we had started, if I did this, let's see here. So if I went, now what is it? Less than 1, because it's a reduction, right? We had an enlargement first, and this is a reduction. Okay, but if I'm going to dilate something, the size changes, but also it has to move from or away, either towards or away from what we define as the center of the dilation, right? So what's going to happen if the center of the dilation is inside of a figure? So for example, what if I had something like this? What if I want to dilate this object? So let's see here, I got a triangle. Let's go, okay. So here's my original object, and let's say that we're going to put the center of the dilation right there. Now what's going to happen? Let's say I want to dilate this, and I want the scale factor to be 2 to 1. We could make a pretty good estimate of what, even just kind of drawing this here, of what the enlarged image should look like, right? How could I start? What if I want to locate, let's label these vertices again, just like before. Let's just call this one A, B, and C, and we'll call the center of the dilation point O. Okay, what could I do? Probably that hasn't said it. What do you think? Well, what could I do? I want to make, if I want to enlarge this using a scale factor. So scale factor equals 2, which is the same as 2 over 1. How could I locate, for example, point A prime? What do you think? It's a very good question, isn't it? Any ideas? Kirk?
Wait, is the middle one O?
The middle one's the center of the dilation.
What is that O?
It's O, yeah.
Can you make a line that goes through O and A, O and C, and then O and B?
Yeah, okay. So let's do this. So let's make a line. Let's make a line that starts at the center and goes through A, starts at the center and goes through B, starts at the center and goes through C. Okay? Now what?
Here, all of them happen like that.
Okay. So yeah, it kind of does it. So now, whatever that distance is, what am I going to do with it? Double it, right? Because the scale factor is 2. Agreed? So we're going to go from there up to about there. Right? Okay. Oops. That's not a wonder. That's going right there. Okay. And we're going to make it red. Okay. And then same thing here, right? Because that has to be the case, doesn't it? Right? We know that the distance from the center to any vertex has to be doubled because the scale factor predicts that relationship also, right? It's not just the side lengths. Okay, so what else do you want to add to this?
Is it like doing a reflection over
I mean, I see where you're going with that. It's kind of, in this case it was because it was 2 to 1. But what if it had been like 3.5 to 1 or something? Then it would have been a little weirder. Then I would have had to measure, okay, what's this distance, and gone out 3.5 times, right? So this is kind of like that. So we're gonna start, because it's 2 to 1, we're gonna start there, and we're gonna go up about there, and then we'll start here, and we'll go to about there. And all we have to do is just connect those points. So there's our dilation. All right, does that make sense? Twice as big. Okay. Yeah. Teacher school. That's where they teach you to do all that stuff. Make sense?
I think it looks like a tunnel.
Yeah, it does. It really does.
Or it's like a pyramid sticking out at you.
Has anybody ever played the game? I can't remember what it's called. Probably. It's just, maybe you have, this is really super, this is like ancient here. Super old school. This is retro to the max. It was one of the first 2 video games made. This kind of reminds me of it. So the first video games ever made were Asteroids. Have you ever seen the asteroid? Like the original, like this little triangle for the ship. And it's, okay, so there's Asteroids. There's another one called, I think it was called Galactica.
Oh, yeah.
Okay, so that's the one where you kind of zoom through space and then you kind of walk through the shapes. You know what I'm talking about? Everyone knows, and you know that.
Yeah.
Okay, so story. The guy that invented that. I went to college with that guy. He was he was an electrical engineer at Stanford. He wrote, and this is before they figured out how to do the royalties on video games. So he wrote this when he was in high school. Just listen, please. He wrote this when he was in high school, and his family grew up in North Dakota, and they were just really, really, really poor, and it was he wrote this video game. He sold the rights to this, I don't know who it was, Atari or whoever it was that bought this, and he still makes so dang much money off this. It's ridiculous. He ended up making just millions and millions and millions of dollars. Comes to school, he stored his Ferrari in our garage. He lived on campus one year. He came to school with a ski-hot depot, and all these toys he brought to school. But he just from writing this one stupid video game. And he still makes tons of money off that. And that wouldn't happen anymore. Because now it's more, you just throw up those opportunities. But just a little side note.
So, because he made
Yeah, no, that's right.
So he made millions off of drawing triangles.
Kind of. It's not a very complicated code either, but he just wrote it. He just was kind of the first person to do it, and he just made a ton of money off it.
How old is he now?
Well,
Because he did that in his like.
he's a little older now. What's that?
Didn't he do that in like 15 years then? It was in college, so it's probably.
Well, he did it in high school.
Yeah.
He wrote it in high school. Yeah.
Wow. Just sold it in high school?
Yeah, he wrote.